Hi everybody. So we're going to look at the mathematics of radioactive decay, specifically the rate at which radioactive nuclei decay, introduce concepts called activity, decay constant, and then in the next tutorial I think we'll introduce half-life. So I want to do a quick little review before we get into it, make sure we understand conceptually what we would expect about decay before we turn to the mathematics. So I'm going to go back to a graph that you produced in an earlier activity. This is the binding energy per nucleon versus atomic mass graph, where we have our most stable nuclei up here. And we learned before that the greater the ratio of delta E to A, the greater the stability of the nucleus. Okay, I know I spelled that wrong, stability, you can spell it right. Nuclei to the left of the peak will produce excess energy for fusion, right? In other words, they'll combine such that they move from the light side up to the peak to a higher ratio. And if you're on the heavy side, it's easier to split to get energy because your daughter particles will be moving that way, okay? So that, if we want to do a calculation of binding energy per unit mass, we could look at a particular reaction. So let's say we have an iron nucleus and protons and neutrons, and we can look at the binding energy per nucleon just to produce the iron nucleus. In other words, why does it have such a high value given this? So if we want to find the mass defect between the constituents and the overall iron nucleus, right? We know that there's 26 protons. That's from that, so we multiply it by the mass of a proton. We have 30 neutrons, and if we do the math, we get this number. And if we want to get the energy, we multiply it by, remember, 931 MeV per U, and we get a total binding energy of about 492 MeV for the iron nucleus. And that doesn't make it high. Remember, the more nucleons you have, you always have a greater binding energy. However, if we do a ratio of delta E to A, so that's going to be 492.4 divided by 56, then we get the 8.79 MeV per nucleon. And that's very high, that's towards the peak, very stable. Now, in terms of radioactive decay, the graph above, okay, and this is important, does not directly indicate whether nucleus will be radioactive or not. Whether something's radioactive or not is another graph that you have on another sheet that looks at the number of neutrons as a function versus number of protons. And if you recall, if we plot that, okay, you should get, ideally you get a straight line, but as you get heavier and heavier, right, this line deviates like that, and then you got a cluster here and here which are radioactive, and then you got a big cluster up there where you got heavy Z's or high Z's. So we're going to look at what it means to decay, what actually happens before we get to the mathematics, and that's what this next blurb about these bullet points. So we know, as mentioned in another lesson, certain nuclei are unstable and are spontaneously, and that word spontaneous is important. If you're asked to describe characteristics of radioactive decay, that's one word you want to add to that. In other words, it doesn't need any input. Okay, so you got spontaneous decay either through alpha, beta, or gamma emission. Okay, those are the only particles that come out of that. Now, if we look at a sample of radioactive material, in other words, an ore, so it's not talking about one nucleus, we're talking about an ore which has many, 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 many nuclei. Okay? One thing we want to understand, and I think you do, but we want to make clear, is that even though that ore might contain gazillions of unstable nuclei of a particular element, let's say uranium-238, they do not decay all at once, okay? But rather, they decay one by one over a period of time. And a good analogy, again, is popcorn, right? So if you place popcorn under high temperature, it, in a sense, makes it unstable. It's going to decay into the fluffy stuff that we love to eat, especially with butter and salt. So as you heat up your collection of popcorn kernels, they don't all pop at the same time. They pop randomly. Okay? And so which popcorn kernel, or in this case nucleus, in a particular sample of ore will decay is completely, utterly, okay, random. In a popcorn kernel, I suppose if you knew the moisture content and all sorts of other parameters, you could predict which popcorn kernel would go first. But for all intents and purposes, it's more or less random. However, and this is the important thing, even though individual events are perfectly random, we can determine approximately how many nuclei will decay in a given period of time using the mathematics of probability. So what's really interesting is that even though radioactive decay, or to a certain extent popcorn kernels, is a random event, given a collection of random events and looking at averages, if you will, you can predict how it's going to behave. And that's what we're going to look at the mathematics of and do an activity to reinforce that. So let's get some definitions about rates of radioactive decay, what you might actually measure. So the first definition we want is something called activity, which is given in this context the symbol A, not to be confused with atomic mass. Okay, so activity is, by definition, the negative, okay, because it's a loss, rate of decay of your nucleus, or nuclei, I should say, because once a nucleus decays, it's usually done. We're looking at a collection of many nuclei, and based on a definition, A is the rate of change of n, where n is your number that you started with, and t is the time over which it occurs. Now, I don't have any units over here. I'm sorry. All right, so if you want to put that, that's just going to be counts, if you have a Geiger counter or number, per second. And if you remember the radioactive buttons, some were setting off the Geiger counter really rapidly, others were less so. That one that was really rapid had a high activity. And the unit for that is called the becquerel, and the becquerel is given the strange symbol, 3 letters, BEQ. I think it's BEQ. Maybe it's BQ, but that's really just numbers per second. Okay, so it's going to have units of something per second. Another very important parameter is something called the decay constant, and that's given a symbol lambda, not to be confused with wavelength. And lambda is not activity. It is, as the name implies, a constant. And it's a property of the nucleus. So different nuclei have different decay constants. And that determines the probability. And eventually we'll talk about where that value of the probability comes from of a particular decay occurs. So a lambda, if it's a really large value, okay, is going to say we have a higher probability that decay is going to occur for that particular sample of nuclei than another nucleotide, a sample of nucleotide of a different element. If it has a low lambda, it's going to have a low probability. And what we understand is neither the activity or lambda, and they are related to each other, are affected by any environmental conditions. And we're talking temperature, pressure, where it is, gravitational fields, etc. And the reason for that is because this occurs at the nuclear scale, which is well below the atomic molecular scale in which these conditions occur. In other words, anything you encounter that's environmental is at most the atomic or molecular scale. And if this decay is a nuclear process, it's going to have no effect on it. All right, so let's get into the numbers. So we can relate A and lambda very simply. So if you take the definition of activity as, again, the negative rate of change of the numbers that you have, right, delta t, that can be related to that constant lambda times n, where n is the number of original nuclei still present. Okay, now that's an exponential, I'm getting a little ahead of myself. So if we want to understand how n changes with time, right, you need to do that with calculus. In other words, if I were to take this and move it to the other side, and what I'm going to do, I'd have negative delta n over n equals lambda t, okay? And if I wanted to solve for that, that delta is like a differential. If I want to solve this, I'd have to integrate this, right? And maybe you've learned that in calculus at this point, where essentially n as a function of t is equal to the integral of all that stuff. Anyway, you don't have to do that, but what we want to understand is when we solve for n, we get n equals n naught, so that's the original amount that you have, okay, times e to the negative lambda t. And that is a exponential decay. Okay, so we're going to see that is a very, very important aspect or property of this decay. And the reason it's a negative, it decreases, is because that negative sign in the exponent. Okay, as time goes up, e to the negative lambda time is going to get a smaller and smaller number, and so we're going to get less and less of our nuclei. But an important thing is an exponential is telling us that the amount we have at any given time depends on what came before that. So after our first time period, we're going to take a fraction of this. And then after our next time period, we're going to take a fraction of this to get a new n. Let's call n prime. And so anytime you have a quantity that moves forward in time, or that changes over time, where the value depends on the previous quantity, that always translates to an exponential, which has interesting properties. Also, since activity is proportional to n, as we saw up here, and lambda is always constant, so that doesn't depend on anything to have to do with the equation. That's a fundamental property of the nucleus. The activity decreases with time as well. In other words, you leave a sample alone, it will get less and less active, and it will be also exponential. And that we could say A, the activity as a function of time, is simply equal to the original activity, e to the negative lambda t, which then if I substitute out a naught, that's simply going to be equal to lambda m naught, right, from up here. Okay, and then it's e to the negative lambda t. So we can talk about how the actual number of nuclei left at a certain time goes exponentially down, or we can talk about the activity. Okay, now, the higher the decay constant, I think I talked about this, right, the more radioactive, and I put that in quotes because that's kind of a vague term, these substances. And we want to understand that the decay constant, even though we haven't solved it here, implicit in this term here is if you're going to take e to some power, the power has to be dimensionless. So if time has units of seconds, then lambda has to be units of 1 over seconds, all right, or seconds to the negative 1. So that's something you want to keep in mind. Anyway, so if you have a large decay constant, that means you're more radioactive. That means you're going to give off things much more quickly. Okay, so the faster it decays, and the faster it decays generally is more dangerous. In other words, high activity is more dangerous than low activity. There's simply more things coming out at any given time. So in the 3 minutes I have left, 2 minutes I have left, let's do a quick one. So I've got carbon-14, which is a radioactive isotope of carbon. Most carbon is carbon-12. It's found in CO2 in our atmosphere. The decay constant for that carbon-14 is a very tiny number, 10 to the negative 12. We can ask how much time elapses before half the sample is still radioactive. And we'll see the significance of half later. So what does that mean? In other words, n after some time equals half of n naught. So now we can apply our equation about how much we have left. We can say, right, n equals n naught e to the negative lambda t. And we know we want half of n. So we can say, I'm going to take the solve for t. I'm going to take the natural log of both sides and move the n naught over there. So I got n over n naught equals the natural log of e to the negative lambda t. Okay, so now we can plug in what we know. We know n over n naught by definition, or what we asked for is 1/2. So we'd say the natural log of 1/2 equals e to the negative lambda t, right? Because the natural log of e to the negative lambda t is negative lambda t. So t is going to be equal to the natural log, let me make sure this, the negative of the natural log of 1/2 all over lambda. And if we put in the numbers, okay, we get, and check this for yourself, it's important you do this, negative 1.8 times 10 to the 11th seconds. That's a lot of time. If we translate that to years, that's 5,700 years roughly. Okay, so for any sample of carbon-14, it's going to take about 5,700 years for half of it to decay. And what will be the activity of the sample at this time? Well, activity is equal to lambda n. Okay, and we know, now n, we're told you have a 1/2 mole. So n is equal to a 1/2 mole, and 1/2 mole is 1/2 of 6.03 times 10 to the 22. Right, that's the number of particles in a mole. That's a number that you should know. And you finish this yourselves.